Hi. Unlike wood beams, steel beams are made of standard sections. So wood, we can add sections or add parts and kind of have flexibility with the wood section. There's glue laminated timber, so you have flexibility in shaping the cross section of your member or beam. For steel beams, you have flexibility, but still your building blocks are standard. So your building blocks here are standard cross sections that everyone in the industry knows, like their names. So they're in beams. They are typically made by either using a wide flange cross section, so it's W sections. Some also refer to it as the H profile. There is the standard American section, S, or it can be also some people called I-beams or I-profile. And there is the C or channel sections. People refer to it also as U sections or U profile. And then there is the angles or L sections. They're standard, and because of that standardization, manufacturers publish or refer to standard like tables for sharing geometric properties of these standard sections. So every type of section, like this one here, has like the W shape or W section, has pages and pages of geometric properties of the different sizes of that section type. So like for example, W1296. So first of all, let's understand the notations here. W is wide flange. 12 is approximately the depth of the section, and we usually for W sections or S sections or C, depth here is referred to the height, the height of the section, not the width of the flange. And then 96 is the weight, and it's not like the total weight because you don't know the length, like the section tables here don't know the length of the beam. It's the linear weight of the beam, so it's a pound per linear foot. That's the weight of the beam. And the tables here for every section provide geometric properties like the area, the depth, in the first and second column, like the dimensions of the flange, the dimension and the thickness of the web. And then for every axis, it provides the geometric property, which we know one of them already, which is the inertia. So for axis, we call here axis X, or here called XX. There is Ix given, and there are two other properties that we didn't see before. But for designing beams, we are interested in one of these new properties, which is called the section modulus. The other property is called R, or the radius of gyration. So we're not covering that in this property in this video, but we are interested into S, which has units of inch to the power 3, and we'll see why we end up with these this type of unit. And let's see here this wide flange subject to a moment around its x-axis, the definition of section modulus here is that section modulus S is equal to I divided by C, and C here is relative to the axis where the moment is applied. So in this case, if I'm dealing with Sx, Cx is measured from the x-axis to the top and the bottom of the section. The section is symmetrical, so Cx, bottom and top, are just called Cx. Now, knowing that sigma is equal to my or mc over I, and S is equal to I over C, so I end up with a kind of a shorter version of sigma, which is m over S. So sigma is equal to mx over sx for a moment mx or for on this cross section. If I'm using the beam not in the right way, but sometimes I will have to use it this way on its side, and the moment now applied is around the y-axis. And this way I'm referring to, or I'm using to, sy, the section modulus around the y-axis. And I can calculate here the sigma, the stresses, as my over sy. So if I'm using a section from the tables, from these two columns I highlighted, I can know the modulus, section modulus for every size. And you can see the units here is inch to the power 3 because it's inertia, inch to the power 4 divided by the distance c, which is an inch. So let's see how we can use this section modulus in an example. So we have here a simply supported beam with a load in the middle of it, 10 kips. And we want to find the most economical steel section to use for this beam, knowing that we have a limited depth here of 10 inch. And we know the ultimate steel stress here and the factor of safety. So the first thing is we need to find the maximum moment. And another simple case of a beam simply supported with a load in the middle. If you want to do the statics and equilibrium, please go ahead. But from practice, people memorize for this case that it's equal to PL over 4. So if I calculate here P and L here is 14, I plug in P equal to 10 kips, L is 14 feet, and use the formula. I end up with the moment here maximum to be 35 kip foot. And it's kind of a triangular moment diagram. So I encourage you to try, if you're still beginning with learning about statics and strength of materials, still starting your career in engineering. I recommend doing the traditional way of calculating reactions and internal moment diagram. But we are interested in what's coming next, which is sizing the beam. So that's an initial step that has to be done. So next is to calculate the allowable stresses, which is equal to ultimate stress over a factor of safety. So I'm reducing my limit here from 65 KSI to 26 KSI. And we need to find now the required section modulus, considering the maximum moment applied on the beam and the allowable stresses of that material used. So sigma max should be less than sigma allow. And I know from the previous slide or board that sigma max, kind of the reduced shrank kind of reduced version of it, its formula is maximum moment divided by S. And I will label here S as my S required because it is the unknown value here. Sigma allow is given and max given, so I'm looking for the value of S required. So if I plug in the values for maximum moment and sigma allowable, I will end up with, I need a section that provides a section modulus, or a size of a wide flange, that provides a section modulus more than 16.15 inch to the power 3. So the fourth step is to find this size or section. So I have to have it strong enough with S more than 16.15 within the constraints, which has a depth of less than 10 inches. And also it has to be economical, meaning that it has to have the least weight. Because the weight of steel translates into the cost of this beam. Because in steel construction, things end up measured by the weight of the steel that's being installed. So I went to the table of wide flanges and picked up a couple of section sizes that potentially satisfy these requirements. So let's see here. I have W6 25 all the way to W14 22. So you have to carefully kind of look at the tables and see what sections can be possibly considered. Possibly here between quotation parentheses. Because if you look here, the last two are not satisfying my depth limitation of 10 inches. So I'm kind of picked the wrong ones. They're not feasible. So the other ones are feasible. But I'm looking after going after the third requirement, which is the economical aspect of it. So all of them are feasible, but I'm picking the one with the least weight, which is W10 19. It has a 19 foot per pound per foot of pound per every linear foot of the beam, compared to, let's say, W6 25 has 25 pound per linear foot of the beam. So W1019 is my recommendation here. Always in design, we're looking for a design option that satisfies the technical aspects of design, which is in our case here strength and S required, and within the constraints applied by the customer, and also economical design. So that's an example of a typical design exercise, and we only focus on that kind of scale of just designing a section of a beam that's subject to this type of loading. All right, thanks for watching, and take care.